Welcome back, folks. We're going to start to do some circuit analysis with phasors. In order to do that, I kind of want to talk about how we get from a problem to a solution. And with these problems where we have time variant, time domain, voltages and currents, and we want to get to a solution, there's a direct path and then there's kind of a more circuitous path. But it turns out that the more circuitous path is a little easier mathematically, so we tend to take that route. Okay, can I get that above my head? There we go. So in general, we want to start a problem. We want to state it as a time domain problem. So it's going to have voltages and currents defined as time domain functions. We're going to have a bunch of components that we're going to need to understand how those voltages and currents excite that circuit, and then we're looking for some value to come out of that circuit, whatever it may be, depending on how the problem is stated. So the direct path requires us to have a very good understanding of differential equations. We can use Ohm's law, not Ohm's law. We can, Ohm's law a little bit. Here we go. We can use KVL, KCL, Ohm's law, the capacitor equation, the inductor equation. There we go. And we can write all of these systems of equations that we've been writing with mesh and nodal and all of those things. We can write those as a system of differential equations. And then we have to solve that system of differential equations, which is fine. There's ways to handle that. What we do as a stepping stone to learning how to do that reliably is we use the phasor transformation. So in this class, we're going to take an alternate path. And that alternate path looks like this. Okay, ooh, I lost my arrowhead on one of them. And we're going to use the phasor transformation, which I've mentioned, and I think we've done a little bit in the videos. And we're going to restate the problem. So it's no longer going to be a time domain problem. It's going to be a phasor domain problem. And, oh, we didn't lose the arrowhead. It's going in the right direction. There it is. Then we're going to use algebra and all of the circuit analysis that we've used up until this point. Everything we've done has been algebra before we started phasors. We're going to get the phasor domain solution, and then we're going to move back to the time domain using the inverse phasor transformation, and we're going to get to the same spot. Okay, so if you want to avoid differential equations, we can use the phasor transformation, restate the problem, do circuit analysis, and then move back. That's what we're doing. Okay, so let's get a problem to practice this with. And let's start out with something that I think we're comfortable with. I hope you're comfortable with it. But let's do this. So here is a nice little circuit. It lines itself up like a voltage divider, doesn't it? And let me grab my text so I don't have to rewrite it. For this circuit, I want to paste it in this window. There we go. For this circuit, we're going to find V out. Okay, so there's V out. Given that V in is 4 cosine, what is that, 10,000 plus 45 degrees. Okay, if you had to do this, we'd have to write out, you know what, maybe I should. We'd have to write out the equation and then solve it as a differential equation. But we could do it. We could do mesh analysis. Okay, we can say this is I of t. Okay, there's 1 KVL, that's all we got to write. How hard could it be? Okay, and we could say V, we go up V in of t, we drop across R times I of t, and then we drop across L di. Let's be consistent, dt. And we're back to where we started, and that's equal to 0. That's a differential equation. Solve it for the function I. It's the algebra of functions. Okay, differential equations is the algebra of functions. Solve it for the function I that makes this equation true. You can do it. This circuit's not that bad, but we can do it with phasors just as easily, if not easier. And certainly as this circuit scales up, it's going to be easier to use phasors. Okay, so when I approach these problems, every component needs a complex number. So if I'm moving from the time domain to the phasor domain, every component gets a complex number. Voltage sources, current sources, get phasors, and any passive component gets an impedance. Okay, so VI is defined up here, and that looks like it's going to be 4 at a cosine of 4 at an angle of 45. Okay, 4 at an angle of 45 degrees, and that's in volts. So that has its complex number. The impedance of a resistor gets a complex number, 1 kilo ohm. Okay, you might be saying, hey, that's not a complex number. Well, it's the real component, right? The imaginary component is 0. So it's a complex number, it's just not a very interesting complex number. So resistors are the easy ones. For the inductor, we have to calculate the impedance. So look at the table from previous videos, and we have j omega L. So we need to know omega, and omega is right there. It's the coefficient of t. So this is going to be j 10,000, I'm just going to write 10k, times L. Well, what's L down here? It's 100 millihenries. Okay, so that's going to end up being ZL is equal to J 1K ohms. All right, so there's our impedance. So all 3 components, there's only 3 components in this circuit, but all 3 components get a complex number. Phasor for the sources, impedance for the passives. Now we do circuit analysis the way we've always done circuit analysis. So this looks like a voltage divider to me. I just made my pen way too big. This looks like a voltage divider to me, so you can go ahead and apply the voltage divider. If you're uncomfortable with that, you can do mesh. I'm going to have an example of mesh in a few videos here. Okay, so let's see. Voltage divider for this one, we're going to say V out. Okay, and it's going to be capital V. Wow, I really screwed up my pen. Where's my ink flow? Here we go. V out. There we go. Look how bold that is. It's capital V out, and it's capital V out because it's the phasor that corresponds with this lowercase v out, which is time variant. So it's the phasor domain equivalent of this time domain value. V out is equal to V in. I want to know the voltage across this inductor, but I use the impedance, right? It's got to be in ohms. So it's going to be J, let me write it symbolically, ZL over the series combination of these two, R plus ZL. Okay, so now we just plug in values. 4 at an angle of 45 degrees. And this is J 1K over 1K plus J 1K. Abusing those SI prefixes, right? Let me scooch over, scooch. Okay. So let's see what that is. So I'm going to encourage you to grab your calculator, whatever calculator you have. I want to make sure that you can get the same value that I do. Okay, so I'm going to make sure I'm in the right mode for my calculator. I have an old calculator that I know and love. I trust the tool because I've practiced with it for years. Hopefully you're getting that same practice with your calculator right now. Okay, 1E3, 1E3. Okay, that looks good. And from that, I get an answer, and I'm hoping that you plugged it into your calculator. Pause the video if you needed to. I get an answer that looks like this, 2.828 at an angle of 90 degrees. Okay, and that's going to be a voltage. So that's good. That's our phasor domain solution. Okay. So if we're looking back up here at our roadmap, we're over here now. Now we have to use the inverse phasor transform to get our time domain solution, because that's what we were asked for. Look at the way it was asked. V out as a function of time. Okay, so we want to get to our phasor domain solution. So we're going to write that as lowercase v sub O as a function of time. Okay, the magnitude of the phasor becomes the coefficient of the cosine. Okay, and now I need the frequency. What's the frequency? Well, the frequency n, these are all linear components. Okay, semiconductors not so much. We don't do those in this class. Next class. The frequency cannot be changed by these linear components. So if I have an omega of 10,000 here, when I pull it back out into the time domain, I have that same frequency right here. Okay, 10,000 as a coefficient of t plus 90 degrees. And the unit on that function, because functions can have units, is volts. Okay, that was your first phasor domain solution. We didn't do any calculus to do that. We did a little bit to derive it, but in this example, we didn't do a single bit of calculus. All we did was use the phasor transformation, do the same circuit analysis that we've always done, and then move back to the time domain. All right. This is the name of the game. You know it gets more complicated. We're going to do a current divider, some mesh, some nodal, all of those things, super nodes, super meshes, all of those come into play. But if you're comfortable with those from the first part of the semester, we're just doing it again with complex numbers. That's it. Okay, current divider coming up next. Maybe I'll pull out a calculator and show you why I hate the TI-84. Sorry, Texas. Hopefully you have a better calculator than that thing. Anyhow, that's what's coming up. Stay tuned and good luck.